Hello class, and thank you for watching the second parts to lesson 6.5, properties on logarithms. In the second part, we're going to begin by talking about the third power rule, or the third property of logs, which is referred to as the power rule. This property here states that if we have a log of some base where a base is going to be some positive number that is not 1, so let me write this down correctly, log of some value base of some element, some value m, and that value of m is raised to a power, to an exponent, which we'll call p, which can be any real number there, then we can rewrite this by pulling that power to the front and multiplying the log base b of this value of m with that exponent p. So these two things are equivalent to each other. Now remember, the equal sign is a biconditional statement, meaning that if this is true, I can write this way, and vice versa. If I see that I have a log base b and I'm multiplying it with some, again, real number, I can make that value and pull that value and make it the exponents to this input value m. So in other words, the logs of a number with an exponent is the product of that exponents and the logarithm of that number. So let's look at some examples of how we apply this property. So let's take this example. So here we have the log base 5 of 7 to the 4th power. So to this property, what this means, because 7 is being raised to this power of 4, we can rewrite this log as 4 times the log base 5 of 7. And that's it. There you have it. There is the property being applied in this scenario. Now, if you look at example B, this one's a little bit trickier because it doesn't seem like this value, which is the square root of x, is being raised to a power, but it actually is. Recall from the prior lessons that anytime we have a root of any value, this can be written as x to the reciprocal of that value's power. So if I have the root of n, I can write that as x to the 1 over n power. So in this scenario here, since this is the square root, I can think about taking the square root of x as x being raised to the 1/2 power. And then applying this power property, I can pull that exponent to the front and multiply the natural log of x with the exponent of 1/2. So this would be the expanded form applying the power property of logs. Moving on to a third example, this one right here, since it's the common log, this would just be 5 times the common log of x. And this again is your expanded form, so nothing challenging about that property again on this third example. And finally, that brings us to our last example. Here we have this one, even though it's not in parentheses, our x is being raised to the 7th power, so applying this property would be 7 times the log base b of the value of x. Okay, so like I mentioned earlier, remember this is biconditional. So if I can do this and pull this exponent and multiply my log with that exponent, I can go backwards. And if I'm multiplying a log with some value, I can make that scale factor, that scalar, into the exponent of the value that we have here. So let's look at example 6a. So for an example 6a, our natural log of x is being multiplied with the scale factor of 1/3. So using this property, in order to condense this, I can write this as the natural log of x and raise x to the 1/3 power. Now, using again the identity that x to a rational exponent is simply a root, I can rewrite this and state that the x, that we're taking the cube root, let me rephrase, we're taking the cube root of x. And that again has to do with having a rational exponent. So this would be the condensed form in the equivalent form of multiplying 1/3 with the natural log of x. So moving to the next example, this would be the log base 10 of 3 to the 4th power, and 3 to the 4th power equals 81. moving along to example C, here we'll have 2/3 of log base 4 of x, which will be the log base 4 of x to the 2/3 power. And again, because this is raised to a rational value, the 3 that we're dividing again this power by means that we have a root, and specifically a third root. So we can write this as the third root of x, and then x is still being raised to the second power. So there you have your condensed form of 2/3 times the log base 4 of x. And that finally takes us to the last example. So the last example, this would just simply be the natural log of x to the -2 power. And because we have a negative exponent, recall from your power properties, if x is being raised to a negative power, we can simply take the reciprocal of that base, which in this case would be x, 1 over x, and that would change the power of the x to a positive number. So if I do that inside here in this parentheses, and get the reciprocal of x, 1 over x, that will change the exponent of a -2 to a +2. And there's your answer. So you'll please turn to the next page. So in example 7, we're not going to use the properties that we discussed in the prior lesson along with this one in order to fully expand a logarithm to multiple logs, depending on how many things we're multiplying or dividing here. Now, the order that we use these two properties when we want to expand, like we want to do here, is to first apply yesterday's property, which is the product or quotient property, and then apply today's property, which is the power property. So we always expand, go in that order there. So like in this example here, we're going to expand by using the product property since we're multiplying the x and the y. So we're going to begin by first writing the log base b of the letter x and the log base b of the letter y. And because we're multiplying, the property here states to add those two logs. So when we expand it by that property, we're going to add those respective logs. Now, since x is being raised to the second power, we're now going to apply the power property to each individual log. So starting with this one. Since x is raised to the second power, we can pull that to the front and multiply the log base b of x with the number 2. Since y doesn't have a exponent, technically it does. Well, technically it does. It has the exponent of 1. We can multiply the log base b of y with that value of 1. But because it's the 1, then it doesn't look any different whether I have the 1 like this or I don't have it at all, because multiplying by 1 doesn't do anything. It looks the exact same way. So this would be also an equivalent form. So this is the expanded form to this. So let's move on to the second example. So here we have the log base 6 of the cube root of x and y to the 5th, but we're dividing the x and the y term. So first let's make sure that we write this again with exponents. So recall that taking the cube root from the prior page, we did an example like that. That's the same thing as x being raised to the power of 1/3. So let's start off by rewriting that part as x to the 1/3 power. Now here, because we're dividing the x and the y, we're going to split this into two logs. So the log base 6 of x to the 1/3 and the log base 6 of y to the 5th. Now, because we're dividing these two quantities, this division symbol right here looks exactly like a minus symbol. So you can use this little mnemonic device, again, this visual aid, to recall when you're supposed to subtract when you expand them, and when you add, when you need to add them again when you expand. So multiplication will add, in this case division will subtract. Now, applying today's property, the power property, I can now pull these exponents on each individual log, on each individual input value of the log, and multiply them by the respective numbers. So here I can write this as 1/3 times the log base 6 of just the letter x, no more exponent, minus 5 times the log base 6 of my variable y. And you don't have to indicate again that you're multiplying like I did in the second example. You could just leave it like the way I have it here. And that would be the expanded form of log base 6 in the equivalent form. So this is the same thing as that up there. So moving on to the next example, this one's a good one here because we have both the two variables of x and y, but both of these are underneath the root of 3. So if it was just x, recall from the previous example, that would mean x to the fourth power, that power of 4 would be divided by 3. But since y is also in that root, that means both of them are going to be, both of those exponents are going to be divided by 3. So let's start by rewriting it like that. So we have the natural log of x to the fourth power, and because that is inside the root of 3, that exponent of 4 gets divided by 3. And then we have times 5, y to the fifth power, and because again the y is raised to the power of 5, but also is inside this root of 3, that 5 is going to be divided by 3 as well. So now splitting this up, this would be the natural log of x to the 4 third power plus, because we're multiplying, that would add the natural log of y to the 5 third power. And again, now applying today's power property, I can pull this first exponent 4 over 3 to the front and multiply the natural log of x with that 4 over 3 power. And then the same thing with the 5 over 3. I can multiply the natural log of y with this 5 over 3 power. And there you have the expanded form of and the equivalent form of this example here. Which now takes us to our last example. So again, this one right here is no different than the one above us, but the only difference is that we have the cube root of x. So we'll write this as the natural log, the square root of x, I'm sorry, not the cube root, square root of x. So that means that x to the third power, that exponent of 3, because it's the square root, and then the x of 2 will be divided by 2, and our y to the fourth power in the denominator. So to split this up first using the quotient property, we'll have the natural log of x to the 3 over 2 power minus the natural log of y to the fourth power. And then again, applying today's property, the power property, I can multiply the natural log of x with 3 over 2, multiply the natural log of y with 4, and this is your expanded form and the equivalent form of this log there. Let's now go in the opposite direction. So for an example 8, we want to now condense this. So to do that, we're going to use those same properties in the opposite order. So step 1 would be now to use the power property, and then step 2 is to either apply the product or quotient property. So therefore, to condense this, first thing we're going to look at is make sure that in front of every log there's no scalar. Like right here we have the 1/2, here we have the 4. So we're going to pull those and make those exponents by the power property. So we have the log of x raised to the 1/2 power plus the log of y raised to the power of 4. So there, we applied the power property. Now we're going to condense this to one log by applying either the product or the quotient property. And because we're adding here an addition symbol, just a little mnemonic visual device here, if I twist it over, that looks exactly like a times symbol. So and there's reasons for that. So because I'm adding here, that means that the x and the y are going to be multiplied together. So therefore we have x to the 1/2 power multiplied with y to the 4th power. And this is the condensed form to and the equivalent form of this log up there. Okay, so now let's look at this example here. So here we have 3 times the natural log of y minus the natural log of x. And we only have one, this first one being multiplied by a scalar that's not 1. So we're going to first move this using the power property and make it the exponents to the variable y. So we have this value right here. Now, even though we don't have parentheses, we can put parentheses around the value of x, so it could be kind of consistent. And now we can condense this to one natural log. And to do that, that's going to require us to divide these two values here, and this time because of the minus symbol. So as a result, we have y to the third power divided by x. So this would be the condensed form to this expression, to this natural log expression right here. Now a little mnemonic device, a little pointer here, little pro tip. The way to know the difference again with multiplication and subtracting and whether you're going to divide or multiply is that with division, notice that this symbol there looks exactly like the symbol that we use. Sorry, I meant to move it. The symbol that we use right here for dividing. So the minus and the division fraction notation look exactly the same for a reason. So there you have, like I said, your condensed. All right, so moving on to the next example, same situation here. This is the only thing that's different is, again, is the base of this thing. We have the log base b of x, but because of that 4, we can make the exponent of x 4. Similarly enough, we have the log base b of 5, and because of this exponent, we can raise that to the to the second power, which is 25. Trying to get my words stuck there together. Now, because we're adding, that means that both of these two values will be multiplied together. So to condense this into one log base b, our x to the fourth power needs to be multiplied with 5 to the second, which I mentioned earlier is 25. And multiplying 25 with x to the fourth looks like this. So there is your condensed form to that log expression. So for this fourth example here, we have 1/2 log base 5 of x, which can be written as, using the power property, log base 5 of x to the 1/2, and then minus, and we can pull this 2 and make it the exponent of y, so log base 5 of y to the second power. Notice that I don't care about the signs on these examples, and I don't pull the negative number and treat this as a -2. I just worry about the 2 itself and just keep the operation between them, because this operation is going to tell me what to do with those two values there. And because I'm subtracting, that means that the x to the 1/2 power is divided by y to the second, which can also be written, because we have a rational power on x. That rational power of x is the same thing as taking a root. And since the denominator is 2, the index to this root is going to be 2. So we're taking the square root of x to the first power, and that's being divided by y to the second. So there is your condensed form to this log expression. So this finally takes us to the last property in this section, which is the change of base property. Now this property is semi-antiquated because back in the 1900s, they had no fancy calculators like decimals in order to evaluate these type of base logs that were not the common log, base 10, or the natural log, base c. So we had to use calculators that had the common log in order to evaluate logs base b of m by using the change of base property, which states that using the common log, this log value here, log base b of m, is equal to the ratio of the common log of m divided by the common log of b. And the same thing would be true if we were to use the natural log. So if I use the natural log of m and divide it by the natural log of b, that would give us the same numerical value as taking the natural log of some base of that m value. So let me contextualize it for you. So here we have the log base 5 of 140. Now, before we didn't have fancy calculators like this decimals calculator here that could evaluate such an example. So here, with this decimals calculator, I can get the log, get the base of 5, and the value of 140, and it calculates the value for me. This key can also be found under your functions key when you scroll all the way down towards calculus. Let me zoom in onto that. Right here, this log with this a underneath it. But if you just simply type in log shift minus to get the subscript, and then type in the 140, you get again the value before. Now, like I mentioned, we weren't able to do that before. And because the only calculators that we had back then were natural, only had keys for natural log and common log, we had the only option to use this property. So we would have to take the log of 140 and not divide that by 5, but divide that entire thing, so by the log of 5. And that gave us the exact same value as you see, the log base 5 of 140. Or the other option was to use the natural log. So the natural log of 140 and divided by the natural log of 5. One thing you cannot do is mix again the bases when you do the change of base. The change of base has to use the same base for both the numerator and denominator. And second, you have to make sure again that you're dividing the natural log or the common log of the actual value by the log, common log, natural log of the base. So in other words, do not do this. This is a very common mistake, that you take the natural log or the common log of 140 and divide the 140 by 5. That is not the same thing that we're doing here. And it's not only true for the natural log or the common log. You see again, it's not the exact same value. So just as long as you don't make that mistake, this again is another easy property to apply. Okay, therefore going just down the line here, like we mentioned, this is the same thing as the common log of 140 divided by the common log of 5, or the natural log of 140 divided by the natural log of 5. So the second example, same thing, the common log of 57.2 divided by the common log of 16, or the natural log of 57.2 divided by the common log of 16. And finally, the last example, the common log of 400 divided by the common log of pi, or another acceptable answer is the natural log of 400 divided by the natural log of pi. So that concludes the second parts to this section on properties of logs. I hope this video was helpful, but if yet you still have questions or stuck or not clear about anything, please message me, or if you're having trouble with the homework, click on message my instructor and I could get back to you as soon as possible. Like always, I appreciate you watching and I hope you have a great day. Goodbye.